This house in Northwich, Cheshire has got a few problems. Thankfully, catastrophic failure like this is rare, but cracking and movement is quite common in old and new buildings. It can occur for a variety of reasons, often due to inadequate foundations or more deep-seated problems in the ground beneath them. Most modern houses have strip foundations. This type of foundation is basically a strip of concrete below all the load-bearing walls. The width of the strip depends on the nature of the ground and the building load. In modern construction, foundations have to meet the requirements of the building regulations. 100 years ago, building control was in its infancy. The requirements were much less onerous than today. Nevertheless, at the end of the Victorian period, new house plans usually showed details of the proposed foundations. Whether the proposals became a reality is another matter. In fact, there are many houses from the end of the Victorian period where the walls, whether brick or stone, were built straight onto the earth. Sometimes the load was spread into the ground using brick or stone footings. A combination of brick and concrete might be found under larger buildings. By the 1930s, most new houses were built with cavity walls sitting on concrete strip foundations. Bylaws, and in London, various building acts as well as bylaws, controlled foundation size. Typically, the strip had to be twice the width of the wall. In London, the 1938 bylaws specified a strip 3 times the width. Not all foundations were strip. This house, from 1935, was built on a reinforced concrete raft because the site, a drained marsh, was unsuitable for strip foundations. A raft spreads the building load over the whole ground floor area. It should be strong enough to remain intact, even if there is slightly weaker ground below part of the raft. In the 1950s, rafts were sometimes used for system-built properties, although ground permitting, strip foundations were still the obvious choice for most houses. Short board piling systems were introduced in the 1960s. They were sometimes used as an alternative to deep strip foundations in shrinkable clays, particularly near trees. The piles were typically 2 to 4 metres deep. A ground beam cast over the top supported the walls. Piling is common today. Since the 1960s, there have been great strides in piling technology, and it can offer cost-effective foundation solutions, particularly on brownfield sites. Where ground conditions allow, house builders will almost always choose strip foundations. They're easy to construct, relatively cheap, and they don't require special equipment or skills. Modern strip foundations are not so very different from their Victorian counterparts, but nowadays they tend to be deeper and are invariably formed in concrete. Foundation problems can be caused by a number of factors. The 3 main ones are settlement, subsidence, heave. Settlement occurs in all buildings as the soil beneath the building consolidates under load, pressing the soil particles together and squeezing out excess water. In sands and gravels, this process happens quite quickly, within a few months. In clay soils, it can take 20 years. As long as the settlement is even, cracking shouldn't occur. The worst that's likely to happen is a fractured drain pipe. Differential settlement is potentially more serious and occurs where parts of a building settle at different rates. Differential settlement commonly occurs in a variety of situations. Whether or not cracking occurs depends on the nature of the construction and the severity of the movement. Many old buildings, for example, built in a flexible lime mortar, have undergone extensive differential settlement, but without showing any signs of cracking. Houses with partial basements are prone to differential settlement. The deeper ground tends to be firmer and less prone to settlement. If houses are extended, either upwards or sideways, a similar problem occurs. Some houses were badly designed in the first place. The size and position of the windows, sometimes made worse by heavy roof trusses, can concentrate loads onto small columns of brickwork. The uneven loading on the foundation causes differential settlement. In some terraced houses, particularly those with ornate bays, the loading on the party walls is greater than the loading on the front walls. If the party wall settles, it tends to pull the front wall down with it. Subsidence is potentially more serious than settlement because it can happen very quickly. It occurs when the ground sinks over man-made or natural underground voids. There are a variety of causes, many of them caused by previous and poorly regulated mining activity.
And what of hearths and homes in the mining district of Dudley in Worcestershire? This is the part of the Midlands known as the Black Country, riddled with ironworks and coal mines that the local folk say have the thickest seams in the country. But the visitors will be amazed at the look of some of the houses. Ceaseless mining operations have caused a subsidence of the ground level, and some of the doorways have a list. Other houses look as if they'd been the scene of a merry frolic and were still trying to sober up. Some lean backwards and some are not quite sure. Cracked walls are a common sight, and this is only a minor separation. Some of the roofs have come unstuck, and formerly very close neighbours are becoming a little distant. The chimneys are beginning to gossip, but happily these old colliers' cottages will soon be no more, for with the march of progress, new houses are to be built to replace them.
Coal is not the only culprit. 80 years ago, this road was level. Droitwich is built on large deposits of rock salt. Natural springs brought the salty water, known as brine, to the surface, where it was collected and allowed to evaporate in large flat pans. In the 19th century, pumps speeded up the extraction process and huge quantities of salt were removed from the substrata below the town. The subsidence is relatively recent, mainly a result of pumping the brine to a new out-of-town works in the early 20th century. This homeowner got a shock when she went to move her car, but found most of her garage at the bottom of a deep hole, which had appeared overnight. It was caused by an underground stream washing away the gypsum subsoil. These swallow holes have been caused by water running through limestone. In clay soils, trees and even hedges can cause subsidence. It's a common problem, particularly in the southeast, where many houses are built on clay. Clay soils contain substantial amounts of water. In long, hot summers, large trees can extract large amounts of water from the clay. As the ground dries, the clay shrinks. A building with foundations anywhere in the root zone can be affected. Minimum distances between trees and buildings should be maintained to prevent potential problems. Mature oaks and poplars are the most thirsty. Poplars, for example, can draw 1,000 litres a week from the ground. The modern trend for off-road parking and concrete patios has increased the risk of subsidence if there are trees nearby in the garden or in the street. Rainwater now runs off the concrete or tarmac into drains and is no longer absorbed by the ground. In clay soils, this can create conditions for subsidence as roots searching for water upset the moisture balance in the subsoil below nearby foundations. In clay, chopping a tree down can cause the opposite problem. With the tree's water demand removed, the clay's water content slowly increases and the ground swells. This is known as heave, and the upward movement can take a foundation with it. Heave can also be caused by a rising water table, flooding, or even by leaking drains. Where drains are broken by the roots of nearby growing trees, an accurate diagnosis can get confusing. In some chalky or silty soils, heave can be caused by frost attack. It's buildings like garages that are most at risk because they have shallow foundations and are often unheated. This 1930s estate was built on farmland, but others were built on redundant industrial sites. These houses, for example, were built on the site of a former colliery. Part of the site was filled with shale, a mining waste. Shales can expand if they get wet, damaging foundations and floor slabs. They also contain sulfates, which can attack foundation concrete. There are other less common but more dramatic natural phenomena which can affect buildings. Landslip can occur where unstable clays, sands and muds overlie stable bedrock. In 1962, a landslip occurred in Lyme Regis. A number of buildings were affected. Natural coastal erosion can also have devastating effects. When built, these houses were some distance from the cliff edge. Earthquakes can be devastating. They're surprisingly common in the UK, although most of them cannot be felt, only recorded by machines. Only 11 people are known to have died in UK quakes during the last 400 years. The last death during an earthquake occurred in 1940 in Criccieth, when a poor unfortunate soul fell down the stairs. When cracks occur in houses, people automatically think of foundation failure. In fact, cracking can occur for a number of reasons. Some of these may be serious, but they've nothing to do with the foundations or the ground below. Problems include sulfate attack, wall tie failure, thermal or moisture movement, lateral pressure from badly tied roofs, defective arches and lintels. And don't forget the less obvious. This wall was hit by a lorry. This wall was struck by lightning. So what sort of cracks suggest foundation movement? Wide cracks running right through the thickness of the wall. Cracks extending down to ground level. Cracks which are tapered. Distorted window and door openings. Tilting external walls. Sloping floors. Where foundation movement is suspected, extensive monitoring and investigation is required. In the meantime, the building may require propping. The investigation, which will normally be carried out by an engineer or surveyor, often includes trial pits, boreholes, soil and root sampling, drain testing, and of course, crack monitoring. A desk-based survey can also be carried out to examine the history and nature of the site. This 1950s estate was built on a site with a checkered history. Glue works, mine shafts, brickworks, and marshes are all shown on an earlier survey carried out in 1903. Crack monitoring can take several months. In the past, glass and mortar telltales have been used. These don't provide much useful information, although they can prove that movement has ceased. Graduated plastic telltales can help identify progressive cracking and can also show if cracks close as well as open. The 3 screws method of monitoring is another option. Measuring between the screws allows for vertical and horizontal movement to be recorded. This telltale also allows for the measurement of displacement, in other words, out-of-plane movement. Once a foundation or ground problem has been diagnosed, repairs have to be considered. There are a number of options. Do nothing, just make good the cracks. Remove the cause of the problem. Reinforce and stiffen the structure. Ground stabilisation. Underpin the building. Demolish and rebuild. In the early 1970s, a stormwater tunnel was constructed to serve South Bristol. The tunnel runs under several houses. 1 or 2 of these developed cracks as the tunnel was being built. This particular property was inspected by a chartered surveyor, following a claim from the building owner who was concerned about a crack below the kitchen window. The surveyor concluded that the damage was of a superficial nature and not structurally significant. In the 1980s, the render was patch repaired. There has been no sign of movement since. Sometimes, where trees or broken drains have affected buildings, it may be possible to patch repair the cracks and simply repair the drain or pollard the tree. But in many cases, the only solution is to underpin the building. This transfers the loads down to a firmer stratum and, if necessary, below any shrinkable clay. In traditional underpinning, in situ concrete forms the new foundation. For obvious reasons, the work has to be done in stages. When these 3 bays have been concreted, work on the 2 in between can begin. If required, steel bars can be used to reinforce the concrete and connect the bays.
This particular job is in Ewell in Surrey, and what happened was there's an extension been added to an older house. Surprisingly, the foundations are quite good. They're at about 1.2 metres, and adjacent to the rear corner there is a rather large tree. It's a 300-year-old cedar of Lebanon. What has happened is that the clay fraction in the soil has been dried out by the tree, and particularly where you have long periods of dry weather, of course the tree extends its root system, and this has caused drying shrinkage in the clay fraction, allowing the foundation to move, which in turn generates the superstructure cracking. During the course of our investigations, we identified that roots from the cedar tree extended to a maximum depth of about 2.5 metres. Piling, of course, is always an option, but on this occasion, because the tree is the primary factor here, the piles, whilst they will support the foundation, won't provide any protection to the floors or any internal walls behind them. The tree roots will simply pass through the piles in the ground and continue to dry the soil out. So that leaves us with traditional underpinning. The underpinning in itself, as well as extending the foundation to stable ground, also provides a root barrier to protect the rest of the building behind it. On this particular case, we have included steel reinforcement in the underpinning design. The purpose of the steel is basically to help bind the underpinning bases together, but it also gives us a certain degree of safety. Should we find any soft ground, we don't have to worry too much about having to dig an extra deep pit, because the steel will enable the concrete to span quite happily even with the load of the building on top. So it does have a quite important function. You can design underpinning without the steel, and if you do that, you just need to consider how you bind your underpinning bases together. This is typically done with a shear key. It's a very simple thing to do. It's just a piece of concrete that juts out of one base into another.
This house, built on soft clay, has a history of cracking and differential settlement. Here, the engineers are using an underpinning system which is safer than traditional underpinning and avoids the need for extensive excavation. A series of short beams and piles takes the loads from the wall and transfers them into the sandstone bedrock a few metres down. The clay is augered, and then a rotary percussion drill forms a socket in the rock for the base of the pile. The beam is reinforced with a steel cage. A single reinforcement bar connects the cage to the pile. The bar is offset to accommodate the tension forces. If access is restricted, this work can be done from inside the house, but this means that part or all of the ground floor may have to be broken up. To cope with more complex problems and bigger loads, cantilever piles might be a better solution. Cracking here has been caused by the changing moisture content of the clay, due in part to several trees around the house. This has affected the ground to a depth of about 3 metres. When the house was built, this problem was not foreseen, so the strip foundations are quite shallow. This system relies on two piles, one in compression and one in tension, and with a reinforced cantilevered beam on top. Although the base of each pile is well below the swelling and shrinking clay, there's still a risk that heaving clay near the surface can pull the pile upwards. A polythene sleeve prevents the soil from gripping the pile. In these houses, the ground problems have affected the foundations and the ground-bearing slab. Piles either side of the wall support a reinforced concrete beam. Unlike the previous system, this solution is relatively straightforward because the piles are solely in compression. The loose ground is well suited to driven piles, and the act of driving can actually help to consolidate the soil. These steel casings are driven into the ground by an impact hammer, and extra sections can be welded on until the piles reach a firm base. The steel casing is filled with concrete, and then the beam is cast. These are angle piles, which can be driven or augured depending on the nature of the ground. They don't require any beams, so the amount of excavation is reduced, and there's no need to cut through the wall. The piles are quick to install and suitable for restricted access. In some cases, piling can be done just from one side. An alternative to underpinning is to cast a beam around the perimeter of a building to stiffen its resistance to differential movement and allow it to act as a monolithic structure. The hoop-safe system, developed by Van L., works on the same principle as the iron bands around a barrel. In a barrel, as the bands cool and contract, the timber staves are forced together by compression. In the hoop-safe system, the compression is achieved by post-tensioning the concrete beams. This system minimises work below foundation level, although additional post-tensioned beams may be required through the middle of the house to keep the structure rigid. In some cases, underpinning is not appropriate. It may be too expensive, or the house may be part of a terrace. In this case, demolition and rebuilding was the only option. The flank wall and rear extension showed signs of extensive vertical and rotational movement, and there were a number of serious cracks running through the walls. The insurance company felt that rebuilding was the most cost-effective option. In some cases, foundation repairs or even demolition are not realistic options. The only solution is to repair the ground. The city of Bath is famous for its beautiful stone buildings. The stone came from quarries and mines in the immediate area. By the 1820s, there were many different mines operating in the Combe Down area, but the industry was poorly regulated and little thought was given to the future. In fact, many of these mines were just closed up and forgotten when they became uneconomic. As Bath expanded in the late 19th century, houses of the new suburbs were built over the old mines. The known extent of the Combe Down mining is shown in grey. Suspected workings are in red. The early miners extracted the stone using the room and pillar method. Chambers were mined, leaving pillars of stone between them to support the roof. Timber props also helped support the ground above. In places, additional pillars were built in loose rubble. The mine showed no obvious problems until 1984, when part of Shaft Road collapsed. A few years later, storms uprooted a tree in a local park, exposing a mine shaft. These ominous signs could not be ignored. The mines underlie a residential area of more than 600 properties. A major collapse, although unlikely, could be catastrophic. Instability in the ground above the mines has been caused by a number of factors. Some of the mines were very close to the surface, sometimes within 2 meters, so they were susceptible to ever-increasing traffic loads and vibration. The pillars were irregular in size and sometimes spaced far apart. To make matters worse, stone has been robbed from some of the pillars, further weakening them. Following extensive survey work in the late 1990s, the local authority developed its Land Stabilisation Programme. The programme approached the problem in 4 ways. Filling most of the voids with foamed concrete, approximately 400,000 cubic metres. Using porous limestone rubble for hydrologically sensitive areas. Using sand for archaeologically important areas. And installing steel supports to protect the habitat of horseshoe bats. This film has briefly explained the main causes of foundation defects and has also described some typical repair options. Most householders want to see major repair work implemented as soon as possible, but every situation is unique and a thorough diagnosis is essential to ensure that the adopted course of action is appropriate, long-lasting and cost-effective.